Let's play a game. I'm going to give you the length and width of 4 rectangles. Your task, decide which one would look the most like a square. Go ahead and think about it. Which one of these rectangles would look the most like a square? Let's think about how you answered. Did you say they all look the same? Did you think larger rectangles look the most like squares? Or did you start doing calculations? In math, we often focus on the final answer, but how you think through a problem can tell us so much more. So let's pause and reflect. How did you solve this problem? When we asked the same question to hundreds of teachers, we saw different lines of reasoning. Some teachers said that all the rectangles would look the same. They noticed that in all 4 rectangles, the length is exactly 3 feet longer than the width, so to them, all 4 rectangles look the same. Others said that rectangle D would look the most square. They explained that when rectangles get bigger, a 3-foot difference becomes a lot less noticeable. Another group of teachers said that rectangle D would look the most square, noting that the ratio of length to width determines the appearance of a rectangle, so the rectangle whose ratio is closest to 1 would look the most square. Even though their final answers were similar, their thinking was different. This is why understanding the reasoning behind an answer can reveal critical insights. So what's going on here? Why were there different types of reasoning involved in this problem? This is because there are different ways to compare quantities that change together. One way is to compare them by asking, how big is this one compared to the other? This is called absolute or additive thinking, and we use it all the time in real life. We use addition or subtraction when we compare things absolutely. But there's another way. We can ask, how many times as big is this quantity compared to the other? This is multiplicative reasoning, and it involves multiplication or division. Multiplicative reasoning or proportional relationships are also used in math and in the real world. When the context is familiar, like comparing prices or making multiple batches of a recipe while maintaining the same taste, kids and adults often do well with proportional reasoning. But in unfamiliar situations, like the rectangles from earlier, it gets a little tricky. In fact, research has shown that recognizing when the situation is proportional is really challenging for students and adults. So here's a simple strategy that can help. You can ask yourself, do the quantities change together? If one increases, does the other also increase? In this example, we're comparing the number of bread loaves we buy and the total cost. We can see that when we buy more loaves of bread, we pay more. We call this type of relationship covariation. You can also ask, what stays constant when they change together? Does the one quantity per one unit of the other stay the same no matter the amount involved? In the same example, if we divide the total cost by the amount of bread purchased, we can see that no matter how many loaves of bread that we buy, each individual loaf of bread still costs $5. Since this relationship is the same across all amounts, this is a proportional relationship. This consistency is called multiplicative invariance. Understanding these two features, covariation and multiplicative invariance, can help students and adults better recognize proportional situations and use proportional reasoning more effectively. So next time you see a similar problem, don't just look for the answers. Ask yourself, how are these quantities related? Is the amount per one unit of the other quantity the same for any amount? Because how you think in math is just as important as what you think. For more research-backed teaching strategies, follow Science of Teaching Math.